In this second module, we are in the process of discussing nuclear physics, and we now turn to a few examples of its applications. In this seventh video, we will briefly discuss two applications, which are radiocarbon dating and imaging by nuclear magnetic resonance. After watching this video, you will be able to describe how one determines the age of organic substances based on their contents of carbon-14, and to describe the principles of imaging using nuclear magnetic resonance. One of the important applications of natural radioactivity is the dating of organic materials by what is called radiocarbon method. This works up to several thousand years and with relatively good accuracy. An example is the very controversial dating of the Torino linen, which some believe to show an imprint of the body of Jesus after his death, and it is shown in this image behind me. Now let us examine how this method dates organic materials. Our atmosphere contains a lot of stable nitrogen-14 and carbon-12, which play an important role in organic processes. The atmosphere is constantly hit by cosmic rays at very high energy. They consist mainly of protons and helium nuclei, but also electrons, photons and neutrons. Cosmic rays interact with atmospheric nuclei. The slow neutrons they produce, among many other particles, can interact with nitrogen-14 to produce the radioactive carbon isotope carbon-14 in a charge exchange reaction. Carbon-14 is a beta emitter with a lifetime with a bit more than 8,000 years, so well suited to date materials that are several thousand years old. At any moment, our atmosphere thus contains a majority of carbon-12 and a small quantity of carbon-14 nuclei. Both of them can form CO2 molecules since their chemical properties are the same. Living organisms like plants consume carbon dioxide for their photosynthesis and will integrate both carbon isotopes alike. When the organism dies, the CO2 ingestion stops. From then on, the carbon-14 component slowly decays, but the level of carbon-12 will stay constant. One thus uses the relative concentration of the two isotopes to estimate the age of fossils. But of course, the concentration of carbon-14 in the atmosphere is not necessarily constant. It depends on the flux of cosmic rays at a given time. And this dating method thus needs a calibration. This curve shown here gives an example of the deviation from linearity of the method. Let us now turn to a non-invasive medical imaging technique that uses nuclear spin. Imaging by nuclear magnetic resonance, NMR, is based on the absorption and re-emission of electromagnetic radiation via the nuclear magnetic moment. The sample is immersed in a magnetic field B0 to establish an external quantization axis. The component of the nuclear magnetic moment along this axis will be proportional to the quantum number ms, which is equal to plus or minus 1/2 depending on the spin orientation. The associated energy is proportional to both ms and B0. The transition energy between the two orientations of the spin, parallel and antiparallel to the magnetic axis, is delta E equal to h bar gamma B0, where the proportionality factor gamma is equal to the gyromagnetic constant times E divided by 2m. The spin vector rotates around the magnetic axis with a Larmor frequency, nu0, which is equal to gamma B0 divided by 2 pi. A photon can thus be absorbed by the nucleus if its frequency corresponds to this resonance in the range of radio frequencies if B0 is a few Tesla. This resonance can then be used to do what is called nuclear spectroscopy, and you see a nuclear spectroscopy apparatus in the image on the right. But let us now discuss how one uses this to locate molecules and nuclei inside your body. By varying the magnetic field around B0 with gradients in all three spatial directions, one can correlate the resonance frequency with the position of a certain type of nucleus. The intensity of the signal is then proportional to the local density of the element. This is the principle of nuclear magnetic resonance imaging, NMR. One uses the resonant frequencies of, for example, hydrogen, sodium-23 or phosphor-31 to obtain an image of the internal structure of the body. Most often, hydrogen is indeed used to obtain access to the density distribution of liquids and soft tissues, which are difficult to render by classical tomography. The patient is introduced into a solenoid or between two Helmholtz coils, as in these two examples. They provide the field B0 of typically a few Tesla. Additional coils adapted to the body region under examination provide the magnetic field gradient. A pulsed radio frequency signal is then applied and its absorption by the tissue is analyzed by Fourier analysis. The height of the Fourier peak at the resonance frequency measures the local density of the chosen nucleus. After a characteristic relaxation time between milliseconds and seconds, the RF signal is restored. The time delay can reveal additional tissue properties. One then obtains an image with a typical resolution of order millimeters and a very good contrast, as you can see in this NMR picture of the knee. In addition, the image shows also the soft tissue, difficult to visualize by classical X-ray tomography. The mechanism of nuclear magnetic resonance even allows for a functional imaging of organs. This is due to the magnetic properties of hemoglobin, which transport the oxygen in our blood. Hemoglobin is found in two different forms. The red blood cells, which are oxygenized by the lungs, contain oxyhemoglobin, a molecule which is inactive in NMR. The red blood cells which have delivered the oxygen to the tissue contain deoxyhemoglobin, which is a paramagnetic molecule. This means that under the influence of the external magnetic field, it will acquire a magnetization which is detectable by NMR. Brain activity, for example, causes characteristic dynamics of blood flow and composition. In active brain regions, where the neurons are stimulated, one observes simultaneously a higher oxygen consumption and a higher local blood flow. In healthy tissue, the increase in blood flow is more important than the local consumption of oxygen. This corresponds to a relative decrease in deoxyhemoglobin, which can be used to localize brain activity. In the next video, we will present another important application, the physical principle of energy release in nuclear fission, which is currently furnishing about 10% of the global energy consumption.